This is a video walkthrough for practice 9.3 using exponential models. In 1 through 8, we're asked to make a table of values showing initial values and repeated operations, and then use that table to write a function rule for the relationship that's described. In 1, the population of a Texas town is initially 4,000 in the beginning of the year 2010 and tripled every year. So we're going to create a table that reflects that. I'm going to let t be the time since the beginning of 2010. So t equals 0 represents the beginning of 2010, and p be the population, which in the beginning of 2010 is 4,000. At the end of 1 year, the population triples, which means it gets multiplied by 3. In the end of 1 more year, the population triples again, which means it gets multiplied by 3 again, which means it gets multiplied by 3 squared, or 4,000 gets multiplied by 3 squared. And then if we multiply by 3 again, then we have 4,000 times 3 cubed. I'm going to go back and insert some other values here. If we look at year 1, t equals 1, 3 is raised to the first power. And in year 0, 3 is really being raised to the 0 power, since 3 to the 0 is equal to 1. That's enough to get a pattern. And so what we can say about p, the population, is that the population is always equal to 4,000 times 3 raised to a certain power. If we look at the powers, when t is 0, the power is 0, and when t is 1, the power is 1, etc. So the exponent is the value of t. All right, in number 2, we have another scenario. Population of a Texas town was initially 4,000 at the beginning of 2010, so I'm going to let that be reflected in the table. T equals 0 represents the year 2010, or the beginning of 2010, and the population is initially 4,000. And then it increases at a rate of 300 people per year. So after 1 year, 300 people are added to the population. Not tripled, right? That's multiplication. This time we're adding. And then in year 2, we add another 300 people. But 300 plus 300 is 600, or 300 times 2. At the end of 3 years, 4,000 will have had 300 times 3 added to it. I'm going to go back and insert some implied values here. In year 1, we're adding 300 times 1. In year 0, we're adding 300 times 0. And so that means that the population in general is always equal to 4,000 plus 300 times the value of t, since that multiplier matches the t value. In number 3, we're still talking about that same Texas town. It has an initial population of 4,000, and it triples every 4 years. So at the end of 4 years, the population will be 4,000 times 3. At the end of another 4 years, so that would be at t equals 8, the population gets multiplied by 3 again, so 4,000 is multiplied by 3 squared. And then at the end of 12 years, 4,000 would be multiplied by 3 to the 3rd power. I'm going to go back and put in some implied values here. That 3 that's sitting there should be raised to the 1st power, and we can write a 3 raised to the 0 power in our initial value. What we need to be aware of is that these exponents this time do not match the value of t, except for when t is equal to 0. So p is equal to 4,000 times 3 raised to the, and whatever the value of t is, it needs to be divided by 4 in order to get the exponent. So P is equal to 4,000 times 3 to the T divided by 4 power. In number 4, a cup of coffee contains 100 milligrams of caffeine, which leaves the body at a continuous rate of 17% per hour. So we're going to write an equation that relates C, the amount of caffeine, and T, the time since ingestion, an hour. So what we need to be aware of is, think of this, what percent remains in the body after each hour? And the answer to that would be the initial 83% or the other 83% that did not leave. So that means that when T is equal to 0, the amount of caffeine is initially 100, and then at T equals 1 hour, 83% is left. So that is 100 times 0.83. And then after 2 hours, 83% of that is left. And so, in other words, we're going to multiply by 0.83 again, or 100 gets multiplied by 0.83 squared. After 3 hours, 100 times 0.83 raised to the third power. I'm going to go back and put some implied exponents in there. 0.83 to the 1 in our second row, and in the initial row, 0.83 raised to the 0 power. So it appears that the amount of caffeine is equal to 100 times 0.83 raised to the T power. In number 5, the rodent population in the city is currently estimated at 30,000. So let's put that that amount in our table. T is equal to 0. The rodent population, R, is equal to 30,000. And then it is expected to quadruple every 5 years. So at the end of 5 years, 30,000 will have been multiplied by 4. At the end of another 5 years, so at T equals 10, 30,000 will have been multiplied by another 4. So 30,000 times 4 squared. At the end of 15 years, 30,000 times 4 raised to the third power. I'm going to go back and put some implied exponents, 4 to the 1. And in our initial row, we have 30,000 times 4 to the 0. What we'll notice about our exponents is that they are all the T value divided by 5. So R, the rodent population, is equal to 30,000 times 4 raised to the T divided by 5. In 6, an investment pays a 4% interest rate compounded quarterly. That's every quarter of a year. $5,000 are invested initially, and no withdrawals or additions are made during that investment period. We're going to write an equation that models the relationship between the value of the investment measured in dollars and the time in years. So when T is equal to 0, there are $5,000. And then at the end of 1 quarter is what we need to be thinking about. And after 1 quarter, we're going to make a gain, but we're not going to make a 4% gain. We're going to make a 4% divided by 4 gain. Since 1 quarter is 1 quarter of a year, the annual interest rate gets divided by 4. So after 1 quarter, we have $5,000 plus 1% of that $5,000. So that would be $5,000 times 0.01. Now I'm going to go back and put an implied multiplier here. That 5,000 that we're starting with is actually multiplied by 1. And if we factor the $5,000 out, we get 5,000 times 1 plus 0.01, or 5,000 times 1.01, which is to say that if we start with 100% of our investment and we add an additional 1%, then we will have, at the end of 1 quarter, we will have 101% of the investment. So after 1 quarter of a year, the amount of the investment becomes 5,000 times 101%. After 2 quarters of a year, the investment becomes 5,000 times 101% times 101% again. After 3 quarters, 5,000 times 101% raised to the third power. I'm going to go back and put some implied exponents. And in our initial column, 1.01 raised to the 0 power. So our exponents are 0, 1, 2, 3, and our times are 1 quarter, 0, 1 quarter, 2 quarters, and 3 quarters. So what we'll notice is that the exponents are 4 times as big as the values of t, which means that the equation must be v equals 5,000 times 1.01 raised to the 4 times t power. In number 7, we have a new teacher digging into his savings account to pay his monthly bills. Each month, his expenses exceed the amount in his paycheck by $1,350. The initial balance in the savings account was $20,000. So we may insert that at t equals 0, that initial time, the amount of dollars A in his account are 20,000. Fix that label there. And then we're representing what happens after t months. So at the end of 1 month, he's going to dig into his savings account and take out an additional $1,350. So at the end of 1 month, the savings account will be depleted by $1,350. At the end of 2 months, the savings account will have another $1,350 taken from it. So 20,000 minus 1,350 times 2. At the end of 3 months, 20,000 minus 1,350 times 3. I'm going to go back and put in an implied multiplication and an implied subtraction. And so it appears that the amount A in the savings account is equal to $20,000 minus 1,350 times t, a linear relationship. In 8, there are initially 700 grams of a radioactive element present. So at t equals 0, which is measured in days, the A amount of radioactive material is 700 grams. The half-life is 8 days. What that means is after 8 days, the amount of radioactive material is cut in half or multiplied by 1/2. After another 8 days, so after 16 days, that amount is cut in half. So 1/2 will be raised to the second power. After 24 days, that amount is cut in half, so 1/2 raised to the third power. I'm going to go back and put in some implied exponents and implied multiplication there, 1/2 to the 0 in the initial row. And what we can observe is that A, the amount of radioactive material present, is always equal to 700 times 1/2 raised to an exponent. The exponents are the t values divided by 8. For 9 through 12, we're going to need our calculator and also the mathematical model. The amount of money is equal to the principal times e raised to the interest rate times time, where a is the number of dollars in a savings account after t years after an initial deposit of p dollars. If interest is compounded continuously at an annual rate r, where r is the decimal equivalent of the interest rate. So in number 9, an initial deposit of 600 is made at an annual interest rate of 5%. How much money is in the account after 3 years? So P is our initial deposit, and the interest rate is 0.05, and T, the amount of money, is 3 years. That's something that we can enter into the calculator directly to find the value of A. So just enter 600 times e to the 0.05 times 3, enter, and round it to the nearest cent. That is 697.10. We should always consider that where money is concerned, rounding to the nearest cent is appropriate. In number 10, if an initial deposit of $500 is made and an annual interest rate of 3%, how long would it take for the account balance to grow to $750? So in this case, our account balance A is equal to $750. The initial deposit is $5,000, and the interest rate is 3%, but we don't know time. So I'm going to start to solve this by dividing by 500. So 750 divided by 500 is 3/2, but you don't have to simplify that. And then this is an exponential equation, so if we write it in logarithmic form, we can solve for the exponent. So the exponent is 0.03t, and that's equal to the logarithm base e, which is a natural log, of 3/2. So that means that t must be equal to the natural log of 3/2 divided by 0.03. That's our calculator ready form answer. And then we can use the calculator to find a rounded value. So I'm going to enter control divide for a fraction. You can probably get away without doing that, but it's a good habit to get into. Natural log of 3/2 on the top of the fraction, which I've entered wrong. I need to correct that. So always look at that screen to make sure that it turned out correctly, and then divide by 0.03, enter. And we don't have rounding directions, but it's safe to say that we should be rounding to the nearest thousandth, unless it's money. So 13.516. And the units on that would be years, since t represents the number of years. In number 11, an initial deposit of $700 is made at an annual interest rate of 4%. How long would it take for the account balance to triple? So if the account balance triples, if our initial deposit is $700, then our account balance would be $2,100. Too many zeros, $2,100. And that's equal to 700 times e to the 0.04 times t, because we are looking for how long it would take, so we're looking for t. Dividing both sides by 700, we get 3 is equal to e to the 0.04 times t. We need to solve for the exponent, so 0.04t is equal to the natural log of 3. That means that t is the natural log of 3 divided by 0.04. That's our calculator ready form answer. And let's grab our calculator and compute that value. So control divide for a fraction, and the natural log of 3 divided by 0.04 gives us a value of 27.465. And again, that would be years. For 12, an initial deposit of $800 is made into an account, and the account balance grows to $1,000 after 5 years. What is the annual interest rate? So our account balance here grows to $1,000, and the initial deposit P was $800. And we don't know the interest rate, but t is equal to 5, so 5 times r is the exponent. I'm going to start by dividing by 800, so 1,000 divided by 800 is 5/4. You don't have to simplify it, and that's equal to e to the 5 times r. And so if we want to solve for the exponent 5r, that's equal to the natural logarithm of 5/4, because that logarithm is the exponent. And so r is equal to the natural logarithm of 5/4 divided by 5. And if we do that calculation, natural log of 5/4 divided by 5 is 0.045. That's to the third decimal place. If we change that to a percent answer, that would be 4.5%. In 13 through 16, the panther population in a wildlife preserve is modeled by a limited growth model. P is equal to 1,000 minus 800 e to the negative 0.3 t. P is the number of panthers after t years. So we want to find the initial number of panthers in the wildlife preserve. Initial means at t equals 0. So P is equal to 1,000 minus 800 times e to the negative 0.3 times 0. This could probably be done without a calculator because e to the 0 is going to be 1, and then we'll just have 1,000 minus 800, which should give us 200. So there will be 200 panthers in the wildlife preserve, but we can certainly verify that with a calculator. And so on the calculator, 1,000 minus 800 times e to the negative 0.3 times 0 gives us 200 panthers. In number 14, find the number of panthers after 7 years. So this is a very similar question. P is equal to 1,000 minus 800 times e to the negative 0.3 times 7. This we definitely will need a calculator for. So I'm just going to redo that same calculation from the previous question, only I'm going to change that 0 to a 7. And now we have 902 panthers. What rounding makes sense would be a whole number of panthers. We probably wouldn't give an estimate using, a tenth of a panther or something like that. In number 15, how long will it take for the panther population to grow to 500? So we are going to replace this time P with 500. And we are looking for the value of t. So I'm going to subtract 1,000 first. 500 minus 1,000 is negative 500. And that's equal to negative 800 e to the negative 0.3 t. Dividing by negative 800, that gives us positive 5/8 is equal to e to the negative 0.3 t. And if we want to solve for the exponent, we need a logarithm to do that. Negative 0.3 t is equal to the natural log of 5/8. So t is the natural log of 5/8 divided by negative 0.3. That's our calculator ready form answer. So control divide for a fraction. The natural log of 5 divided by 8, and then divided by negative 0.3, and that gives us 1.567. I think it's safe to assume that we can round to the nearest thousandth, since this is neither money nor panthers, and so 1.567, and that would be measured in years. The last one's kind of an interesting question. How long will it take for the panther population to grow to 999? So I'm going to replace P with 999, and then we'll solve for T. And so subtract off 1,000. 999 minus 1,000 is negative 1. And then dividing by negative 800, we get 1/800th is equal to e to the negative 0.3 times t. If we want to solve for the exponent, negative 0.3 t is equal to the natural log of 1/800th. And then dividing by negative 3, we get natural log of 1/800th divided by negative 0.3. That's our calculator ready form answer. And we had a similar calculation in the previous question, so I'm just going to edit it. So the natural log is of 1/800th and divided by negative 0.3, and that gives us 22.282 years. This is a limited growth model, which means that the growth can happen quickly at first, but then tails off quickly as the number of panthers approaches its limited capacity of 1,000 in the wildlife preserve.